velocity in the x direction. And then we defined, yeah, we just said that was 1. Here, let me, here, I'm going to clear this. So we might have gotten kind of convoluted with all the stuff that I had lying around, but let's take another easier example. So again, we're going to say that y, yeah, so like you're seeing me write, but you aren't hearing me say it for a while. Yeah, I think I'm just going to put a whiteboard on my wall. It's got to be easier. And then you guys can just watch and you'll hear me, and I don't know where you can type, but yeah, we'll use something else. You has a fix. Eric has lots of fixes. What do you think? I'm just trying to illustrate this again for you a little more simply. So, we have the same situation. There's some path, y and x, and we'll define it like that with y equals 1/2 x squared. And then and there's a particle moving along that path, and it can move along that path with, a particular velocity that we can define. And we'll define that velocity as, we'll just define it in one direction. So we'll say in the x direction, the velocity is equal to some constant c. So what's that actually saying? That's dx dt equals c. So what do we get when we integrate? X equals c times t. So that's how fast it's moving. That's its position with x. And how fast it's moving with x is just that constant c. And the crux of what I was trying to show you was just how to use the chain rule, so that if I give you a function defined in x, but you need something that relies on t, you can get to that. And you'd be able to do this even if you didn't know how to integrate this to get to ct, like if it was a more complicated function than just a constant. You really don't need to be able to integrate to the position to find the displacement in the y direction. So if I want the velocity with y, that's going to be equal to dy dt. And dy, dy dt is equal to dy dx. Okay, yeah, c's a constant. You can call it 5 if you want. So that would be equal to 5t. So yeah, dy dx and then dx dt. So that is the chain rule, and that works in a number of ways. That's kind of how you get like our fancy differential equation problem. There, you use the chain rule there, and it's basically just saying that if you take the derivative of some function that has some other function inside of it, then the derivative is going to be the derivative of the outer function times the derivative of the inner function. So, I mean, if I told you that, g equals x cubed and h equals the natural log of x, and then I give you the natural log of x cubed, and I want you to differentiate that, then it's simply the natural log, the differential of the natural log of x cubed, which is 1 over x cubed, times the differential of x to the third, so 3x squared. So you end up with 3 over x. Did I do that right? I hope so. But that's the chain rule. Albert, help me out, is that right? Well, anyways, so dy dx would be the derivative of the y function, which is 1/2 x squared. Okay, good, thank you. With respect to x, and then we know that dx dt is equal to c. And like I said, it doesn't have to be c. I could give you some really ridiculously complicated function there, and you wouldn't have to integrate it. All you'd have to do is plug it in here. So that's the nice thing about it. But in our case, it's really easy. So dx dt is just c. So we end up with the derivative of 1/2 times x squared is going to come out to be x, and then c is c. So it's equal to c times x. And we know that x is equal to c times t. So you could do that, but again, depending on the question, it's enough to say that it's just c times x. And you could put that in here. So if we had our Vx equals c, and Vy equals Cx. Yeah, you could have. But that makes it way too easy though, Albert. That's like, turns it into a 2-second problem. I wanted to take an hour talking to you about it, so. But yeah, you can plug in and solve it that way. Yeah, the issue just becomes when you get into more complicated problems. So if you hadn't been able to find x easily, then you wouldn't have been able to substitute it in easily, and you would have wanted to do it this way. The acceleration, so we need to take the derivative again. So if we had put it in to this form, then we know the derivative of y with respect to t is just going to be c squared. What can I erase here? Is there any way we can get rid of the x and cx without the integral of vx? If you don't know x, I think you're going to be hard-pressed to replace that with anything with t. But again, that's why we use the chain rule, so that you don't have to in this instance. Okay, so we want the derivative of the velocity, again in the y direction only, because we already know that that acceleration is 0 in the x direction. And we want that with respect to t. So we could do two things. We already know, like I said down here, we know that it's c squared t. So that's simply c squared. But if we didn't know x, or if it wasn't so simple, then we can do, again, the chain rule. So that's going to be the derivative of the velocity in the y dx times the derivative of x dt. And that's going to give you derivative of cx dx times the derivative of x derivative of time, which we know is c. And then the derivative of cx with respect to x is just c. Because anytime you've got just a constant times a variable, you take the derivative, you're left with the constant. So c times c is c squared. So you get the same answer either way. You get the same credit either way. But if you were given a more complicated function, you'd want to be able to do it with a chain rule. And I'm going to give you a more complicated function on your test. So let's make sure we know how to do that. Not to say you still couldn't figure out how to integrate it and do all that, but it's just faster if you know how to do the chain rule. I'm glad I remember how to do calculus. Are there any questions on that? So if you take anything away from that, it should be this. Yeah, exactly. When in this case, when we derive again, then the x is going to go away, and then we're left with whatever we had as our dx dt before. So that way, if it's a really nasty, complicated function, then you're bypassing having to worry about that. But yeah, definitely take this away as the chain rule. And you can practice it on simple functions, like I did with the natural log of x cubed, or if you want a really simple function, you can do something like e to the x squared, since the derivative of e to the x is just e to the x. That's a pretty easy one to work out. Bigger size. Okay, so if you want to practice, you can just use simple functions like that, and your calculators can tell you if you're right or not. Or you can also go online and plug it in, and Google will even integrate for you, I think. I don't know how calculus teachers give homework anymore, if there's websites that'll do your calculus for you. But I know you can make it more complicated than just solving the problems. But anyhow, oh God. So, yeah. Okay, that's better. So e to the x squared, if we want to take the derivative of that, so the derivative of e to the x squared dx. So what do? We get e to the x squared, because that's the derivative of that if you ignore the x. If you just say that x squared, like u equals x squared, so now we've got e to the u. So the derivative of e to the u Change tabs. Oh, that's cool. Oh, okay. So are you guys seeing the tabs that I'm changing though? Like, do you see that me writing this now? Or are you guys still on the other tab? Oh, sweet. Yeah, this is really neat, Eric. I'm glad you knew about this and showed it to me. But anyhow, whoa. So, see, anyways, you would just say that a dummy variable like u equals x squared, so what you actually get is e to the u, and then the derivative of e to the u is just e to the u. You plug the x squared back in for the u, and you get e to the x squared times the derivative of u with respect to x. And the derivative of u with respect to x is 2x. So you end up with 2x e to the x squared. No, not plus c. You guys got me all paranoid about my plus c's. So that's if you want to practice with the chain rule. That's how you do that. So I'm going to leave that behind. And we can... All right, so I'm going to change to the next tab. There we go. Keeps going back. Okay. Okay. Does anyone have a question? So that's the chain rule, and I'm going to talk about that again tomorrow in class, and then we can talk about it more. We'll do one of these again tomorrow night. And I got to tell you, the multiple choice that you're going to see is going to be it's all stuff you saw last year. Letting us all change this is a little goofy. All right, so it's going to be all stuff that you saw last year on the multiple choice. It's going to be the free response questions. They're going to be a little challenging. And there'll be one that's going to be like what I just showed you. So you need to be able to use the chain rule to be able to find out the velocity and acceleration when I give you a position with respect to time. I hope somebody's actually just changing those and it's not cycling on its own. Maybe it's because I'm waving the pen around. Anyways, and then the other one is going to be that differential equation problem with the acceleration. So I put some notes up about the differential equation problem, and what I gave you in class should explain why it's set up the way it is, and then how you actually do solve it. But I just wrote some notes telling you kind of the reasoning behind why you want to set it up that way. And basically, and you can see this in the notes, but you want to recognize that like 1 over x is the integral of that is ln of x, right? Okay. So let's stop rotating screens. So it's the integral of 1 over x is the natural log of x, and so when you when you have that differential equation problem, we're using basically the chain rule again, because we know that if we can get it to where it's sorry, that's actually supposed to be dv dt over v, then we know that that's actually, when we integrate, that is ln of x. V is some function of t, so when we differentiate, or x, it's v, ln of v, sorry. So we know when we differentiate ln of v. With respect to t, we get 1 over v times the derivative of v with respect to t. So if we can get it towards dv dt over v, we can suck that dv dt back in when we do the integral, and we end up with just ln of v. In the case of the problem that I gave you, it's actually going to be ln of v plus something because of the way the problem's set up. And that's all in the notes that I gave you and in the handout as well. So are there any questions about that problem? Which, again, we'll talk about tomorrow. But if you want to dig into it now, we can. And we should probably call it in about 15 minutes at 9:30, which is a little longer than I wanted to go, but that's okay. Multiple choice and then free response. So it'll be about 19 multiple choice questions and 2 free response questions. And I'll give you 25 minutes for the free response, and then 25 minutes for multiple choice, and then you'll have the rest of the time for the free response. So you should have about 25 and 25 probably. 25 minutes and 25 minutes. Are there any questions about, now multiple choice is almost entirely conceptual. I ran through it and did it all in my head without a calculator. You know, the questions are not, they're nothing you haven't seen, they're nothing you didn't see last year. So I don't think you'll be surprised by anything. So if there were any areas that you're struggling in or anything you're unsure about, just let me know and we can work out some problems for that. Okay, so yeah, just definitely check out the chain rule and get kind of comfortable with that. And remember, it doesn't have to be a complicated function you can replace, because in this case, we just basically replaced v. So we said that's u equals v. So that's like, you know, ln of u. And then we took the derivative, so we got 1 over u times du dt, but u is v, so that changes to a v, and that changes to a v. So it doesn't have to be complicated, it can be really simple like that. All right, so thanks very much, Eric, for pointing out this website. You know, that's great, and we'll try that other one you were talking about tomorrow so more people can join in if they want to. And then I'll see if there isn't maybe a better website that we can use besides this. He left? Oh no, he was so helpful. Well, anyways, I'll see if there isn't a better website we can use so that the text and the screen can just be, well, maybe the one he's on has text as well. But I'll see if there's just a better website we can use so I can just link you to it instead of having all this craziness with an event and inviting and all that. So yeah, he was saying, yeah, dabble board. So we'll try that, and I'll broadcast my voice over over something else. So yeah. And I'll work on my handwriting with my fancy digital pen. You really do get used to it pretty quickly. The multiple choice will be easy. The multiple choice should be pretty easy, and then the free response is going to be pretty hard. So if you ace the multiple choice, yeah, no problem, Frank. If you ace the multiple choice, then you should get at least a C, even if you bomb the free response. But hopefully everybody will do pretty decently. Well, I mean, the multiple choice is right or wrong. The free response, it's going to be similar to an AP question. So I'll kind of look at their rubric and see how much they count different things, and we'll go from there. But yeah, you'll be able to get partial credit on the free response. On a test, I'll definitely take the time to go through and wow, the size of the board's changing now. But yeah, on a test, I'm definitely going to take the time to go through your free response and give you partial credit and things like that. Okay, no problem. Bye. Let's see. Yeah, no problem, Albert. Thanks. Yeah, Amanda, if you're still there, if you want to do more calculus, we can do some calculus for a few minutes. Okay, awesome. All right, cool. We'll do that tomorrow, and then we'll have another review session tomorrow night too. And we'll talk about that more in class so we can make it a little more productive. All right, good deal. Good night. You're very welcome.